Okay, let's look at this one. A little bit different. It says, so you might have had a different quadrant, but this says sine is 4/5 and alpha is in quadrant 2. So we need a picture here that kind of represents that. And we know we're dealing with triangles, right? Triangles. We've got our relationships about opposite, hypotenuse, and adjacent. So it says quadrant 2. So let's draw top half of the circle here. And so sine is 4/5. So we could see that as what? Opposite over hypotenuse. Right? Opposite over hypotenuse. So might be something like where this would be the opposite side. So that would be like, we could say that's like 4. And the hypotenuse is like 5. So this would be a circle of radius 5. So this is 5, 0. A negative 5, 0 over here.
So the cost of exponents.
Okay, and so then we would be talking about this angle right here, alpha. And then so then that would fit all my picture now fits the description they're giving you, that the sine of alpha opposite of hypotenuse would be 4/5. Alpha's in quadrant 2, and then it's asking for cosine of alpha. Okay, so we would need what? We would need adjacent. So adjacent over would be adjacent over hypotenuse. And so we need to solve this triangle, right? We can use the Pythagorean Theorem and get this other leg. So adjacent squared plus 4 squared equals 5 squared. And we could solve for that right there using the Pythagorean Theorem. And we would get 3 if we did that. This is a very common right triangle, 3, 4, 5 right triangle. So therefore, the adjacent over hypotenuse would be? It would be 3 over 5, but quadrant 2 for cosine, right? So cosine then would be like negative 3/5. So it'd be the adjacent over hypotenuse, but they're specifying you're in quadrant 2. In quadrant 2, cosine is negative. So this would be negative 3/5. So this is kind of backwards. It's like they're giving you sine, and you have to set up the triangle, and then recognize that in quadrant 2, cosine is negative. Okay, questions about that one? Okay, so let's look at some applications here, real world applications of, I think you saw 1 or 2 kind of easy ones. So here's a, this is an piece of equipment here that measures what's called the angle of elevation. So angle of elevation is an angle swept up from horizontal. It can be in any, doesn't have to be from the 3 o'clock position. Just any angle swept up from horizontal is called an angle of elevation. We've got 39 degrees here. And that piece of equipment is 70 feet from the tree. And what's our goal? The height of the tree. Okay, the height of the tree. So we need a triangle. So can you visualize where the triangle is in this situation? So is the one side of the triangle along the ground? Is one side of the triangle along the ground? Yeah, it'd be 3.5 feet above the ground, right? Because that angle is swept from this horizontal line that's up from the ground. So this is the triangle that you have to see here. This kind of reddish triangle here. And what do we have? So we have this angle. And then we got to decide of adjacent, hypotenuse, and opposite. What do we know? What do we want to know? So we've got this angle 39. So what do we know and what do we want to know? of adjacent, hypotenuse, and opposite? We know adjacent, right? We know adjacent. The adjacent is 70 feet. And what are we after? Opposite or hypotenuse? So we're measuring the height of the tree. We're measuring the height of the tree. So we want the opposite side, right? So we could find this. We could find the hypotenuse, but we're not really. That's not really of interest. The distance from the piece of equipment to the top of the tree on the diagonal line. We could find it, but we're more interested in this side of the triangle over here, which is our opposite. So then we ask, which relationship brings together the angle and the adjacent and the opposite side? Which relationship does that? Tangent. So we're going to do the tangent of 39 degrees, and that's going to equal opposite over adjacent, 70. So therefore that opposite side of the triangle is 70 times tangent 39. And so this is for your calculator now. And make sure your calculator is set in degrees. Make sure your calculator is set in degrees. 70 tangent 39 degrees. And we get? As soon as you get it, tell me.
56.685 degrees.
Degrees, right? 56.685 degrees. Yes? Feet. No, this is the opposite side. It's the length of the opposite side. It's not an angle measure. So we're in feet. Okay? And that's the height of the tree, right? No, that's the height. That's the leg of this triangle, right? So that's from here to here. So to get the height of the tree, add the 3.5 at the end. Is that 60.185? 60.2 feet. Questions on that example? Okay, so that's an idea of angle of elevation. Any angle swept up from a horizontal line. Any angle swept up from a horizontal line. So then there's angle of depression, which is any angle swept down from a horizontal line. Okay? So what's a little trickier about angle of depression is students will get the triangle that in the situation, and they will mistakenly call this angle the angle of depression. Okay? It's not. That's not the angle swept down from horizontal, right? That's the angle that would sum to 90 degrees from the angle of depression, or what's called the complement. It's called the complement of the angle of depression. It's not the angle of depression. The angle of depression is always the angle swept down from horizontal. Swept down from horizontal. And do you see how this is not that? Okay? But it's easy to fall into that trap that you'll label this angle as an angle of depression. It is not. Okay? Be careful for that. Okay? Example? Ship has let out its anchor 200 meters to the ocean floor. Its angle of depression is 53 degrees. What's the depth of the water? Go. So what's the depth of the water at this part of the ocean? So here's what you got to watch out for. So here's a common mistake. You draw this triangle right here, which is a legitimate way to approach it. Then you say, this angle right here is 53 degrees. Is it right? No, that's not the angle of depression. That's a very easy thing to do, though. That's a lot of students will tend to do that. So either you use a different triangle, or you recognize, well, that's not 53, but what is 53 in this triangle? This down here, right? Because your angle of depression is this one here, 53 degrees right there. So either use this triangle over here that I'm outlining right now, or recognize that this angle is also 53 degrees. Those are called alternate interior angles. Alternate interior angles. But the mistake that you want to avoid is to call that the 53 degrees. Angle of depression is angle swept down from horizontal. Swept down from horizontal. Okay, so what do we have? What do we want? We have the angle measure, and of opposite adjacent hypotenuse, what do we have? She said hypotenuse. Agree with that? We have the hypotenuse, which is? We want what? The depth is which side of the triangle? Opposite or adjacent? Opposite. Relationship that brings together the angle measure, the hypotenuse, and the opposite is which one? Sine. Sine of the angle measure equals?
X over 200.
Yep, x over 200. (200 sine 53 degrees) equals
159.72
units on that? 160 meters deep. Questions on that? Okay, so now something harder. So this is the Matterhorn. What country is the Matterhorn in? Anyone know? Norway? Austria? Somewhere in Europe. Is it Africa? I think it's in Europe. Okay.
It is in the Alps, so it's in
Switzerland? Switzerland. Okay. I was closer, Austria. Okay, so here we go. So here's the deal. We want to know how tall it is, but we can't get to this point. We cannot get to here or know how far it is to here, which is the point directly below the peak because it's it's in the middle of the rock, right? It's underneath the ground. So what you can do is you can take two measurements. You can come out here some distance to the side and take a measurement to the top, and they see they've done that as 35 degrees. And then you can move away. So they've moved away 1,500 feet, and they took a second reading of the angle measure, and they got 30 degrees. And so from this information, we're trying to figure out how tall it is, right? So we're trying to figure out how tall is this mountain. Because we can't directly measure how far we are. Like with a tree, we can say, oh, we're this far from the tree. We can't do that with a mountain, right? We don't know how far it is inward, but we can do this. We can take an angle measure, move away, take another angle measure. This is practical, right? How tall is the mountain? So now this is very doable, but it's a multi-step process. It's a harder kind of process than the two easier examples we just had. So I'm going to give you some time to work on this while I take attendance, okay? So You can do it. Put your heads together. Takes a little, you want to be engineers, right? This is engineering. So you're figuring it out, right? Figuring it out.
Yes and no.
And so what's that process like? You try stuff, right? You try stuff and you do correct mathematics and you keep trying stuff until you find a way to do it. Tell me, what'd you do? Tan of 30. Tan of 30 equals what? What's our tangent relationship? Tangent equals what over what? No, it's not a calculator. It's no calculator right now. Tangent equals what over what? Right. So in this triangle that has an angle 30, what's the opposite and what's the adjacent side? No, opposite. Opposite. What is it? Opposite side is length. You're looking right at it. Opposite side. H. And what's the adjacent? Okay, and how would we express that? X. There you go. Tangent 30 equals h over x plus 1500. Okay, what else can we do? Yeah, Brock.
You can do tangent of 35.
Tangent of 35.
That equals
H over x.
And then from there you can do x plus 1500
Uh-huh.
minus tangent of 30 is equal to x times tangent of 35.
Good. So now you're right. So he's saying solve this for h, which just means multiply this up, and solve this for h, and multiply this up. And now h is the same. So therefore x plus 1500 is h, or times tangent 30, that's h. So that has to equal what? X times tangent 35. You're home free, right? You're home free. You can solve for x, and once you know x, you can go back and get h. I'm going to stop there. You can do it. Did anyone work through that and get an answer? Nice enough. 4,000. Anybody else get that? Anybody else get 4,935.8 feet? How do you get that? You solve this equation for x first, and once you have your x, you go back and say use this one and plug your x in and solve for h. Just algebra. It's just algebra and computation from here on out. Here's the key, is getting to this point right here. The rest is algebra. Solving for x and plugging things in correctly. Make sure your calculator is set to degrees, right? Make sure your calculator is set to degrees. Any questions on this?
So in this case, you can't find the opposite of 30 with a smaller triangle. That won't work because it's not a 90-degree triangle.
Are you talking about this right here?
Yes.
It's not a right triangle.
So
These relationships only work for right triangles. Have to be right triangles. So no, that will not. If you do that, what you're going to find is what you just found is this length, which is nothing even close to this length. You see that? If you do tangent with the 1500 and the 30, you're getting this, which is a far cry from that distance there. So yeah, only right triangles for these relationships. Other questions? Okay, let's move on to what's called identities. So what's the difference between an equation and identity? An equation so in this course, when we see variables, we think about all the possible values that variable could take on, right? Variables vary. They take on different quantities, or take on different values, okay? So x can take on many values, but not all values of x make the equation true. So x could be 0. That's fine. It just doesn't make this true. X could be 1. And then what do you get? You get -1 equals 5. Well, x can be 1. It's just that it doesn't make this true. Okay? So in this case, if we were to solve, you get 2 values of x satisfy this equation. Okay? That's what we call an equation. In this case here, this looks similar, okay? But if we do some math over here, look at the right-hand side. If we do a little math, what do we get? Distribute. 1/2 x times 6x is?
8x squared.
Yep, and 1/2 x times -8.
4x.
And what do you notice?
Bang. Gosh darn.
So you notice that it's the same thing as the left. So now x can take on many values. Which values of x make it true? All of them, right? Why? Because every value of x makes this true. Because both are essentially 3x squared minus 4x. Both sides are essentially are this different forms of the same expression. Okay, so this is what we mean by an identity. An identity is where no matter what value you choose for your variable, it always makes the equation true. That's what we mean by an identity. And so these come up in trig. They're very prevalent in trig. Okay, makes sense the difference between an equation and an identity. An equation, only certain values of x will make it true. An identity, any value of the variable that you pick makes it true. Okay, so here's an example. The most common identity is this. So we got our circle here. Sweep an angle, any angle, okay? What is this distance right here? What is that distance right there? Well, it's labeled the opposite side, but what is the distance? What is that length? Sine of theta. It's the vertical distance to the point on the circle from the horizontal diameter as a fraction of the radius length. What about this distance right there? Cosine. And since the cosine and the sine make a right triangle in the circle, and what is this distance right here? But what are we measuring when we do sine and cosine? We're measuring as a fraction of the radius, right? So what is that length right there? If this is sine and this is cosine, then you know what this value is. What is that value? Yeah, and you know what it is. If this is sine and this is cosine, 1. Right? That's 1. It has to be 1 because I'm saying sine is some fraction of the radius. Cosine fraction, no matter what the radius is. So now if we use the same unit of measure, this is a whole radius. And so it's 1. And so we can use the Pythagorean Theorem and we can write that cosine theta a squared plus b squared equals c squared, which is just 1. 1 squared is 1. Is that true for just some angle measures theta or all angle measures theta? So if I choose a different angle measure, I get a different triangle, but does that relationship hold? So I'll do it in red here. So what about for this triangle right here? Does that same relationship hold for that triangle with a smaller angle measure? The red one. It's still cosine theta is still our horizontal distance, sine theta is still our vertical, and we still have a hypotenuse of 1. So yes, it still holds.
No, you gotta delete that.
I can hold it up there a little longer if you want.
Yeah, that'd be nice.
Okay. So what about for this angle here? Does cosine theta plus cosine theta squared plus sine theta squared equal 1? Yeah. So this is an identity, right? Because it's for all angle measures theta, not just some, not just one or a couple, but for all angle measures theta, no matter what angle measure we sweep, we get a right triangle that has this relationship holds true. So this is called the Pythagorean identity. It's the most common and prevalent identity in trig. And another way to write these squares is to write. You'll see it this way. This means the exact same thing. It means find the sine of theta and then square it. Find the cosine of theta and then square it. Okay, here's another example of common identity in trig. So any questions about the Pythagorean identity? It's the one you'll see the most often, okay? Here's another one. So remember we talked about horizontal shifts. Which is this, sine or cosine? Okay, so that's sine. So now if I want to is this ahead or behind the original sine that I drew? Ahead or behind? Is it starting and transpiring before, or it's starting and transpiring after the original sine curve? Before, right? So angle measure from left to right. Here comes the angle measure. Boom, this one starts before. And then the sine starts later. So, is this angle measure, we're going to add or subtract? How much? How much ahead is it? By what angle measure is it ahead? Not pi. It's ahead by a quarter period, right? Which is? So the blue one is sine of theta plus pi over 2. But if you look closely at the blue one, we have another way to express the blue one. Anyone recognize what the blue one is? It's cosine, right? It's cosine because it starts at the max, here at 0, and then goes down to the midline. So that blue graph that I drew, it's ahead of sine by pi over 2, so we can write it as sine of theta plus pi over 2. But it's exactly the same as cosine. So that's an identity. This is true for every angle. Every angle measure that you would pick, the sine of pi over 2 plus that angle measure is equal to the cosine of that angle measure. So these kind of relationships are prevalent with all these sine and cosine and trigonometry. We get lots and lots of these. Here are the most common ones. All right, so you're not going to have time to write them down. Lots of these we've seen some of these already. So Pythagorean, we just talked about the Pythagorean identity. It comes from a right triangle inscribed in the circle, right? We just talked about this one. And similarly, you can look at a cosine curve that lags behind by pi over 2, and that's the same as sine. Okay, so those are identities based on shifting the graph horizontally. Okay, these we've seen already. The right triangle, sine opposite of hypotenuse, cosine, those are identities. Those are identities because they work for all angles, all angle measures. Okay, so then there's the cosecant is another thing, and it's basically the reciprocal of sine. It's 1 over sine. So you see that down here. 1 over sine is cosecant, therefore it's hypotenuse over opposite. Similarly, the secant is 1 over the cosine. So since cosine is adjacent over hypotenuse, the secant is hypotenuse over adjacent. And then the cotangent is the reciprocal of tangent, so it's adjacent over opposite. So all these on the right here give us three new trig relationships called cosecant, secant, and cotangent, which come directly from sine, cosine, and tangent. They're just the reciprocal of each of those. Okay, here's opposite angle. You don't really see those used too often, but these you do. Okay, so these are the double angle identities. We don't have time to prove them, but they do show up. Sine of twice the value of an angle is 2 times sine x times cosine x. And then for the cosine of twice the measure of an angle, there's actually 3 versions of that. Cosine squared minus sine squared, 1 minus 2 sine squared, 2 cosine squared minus 1. So open up into module in your workbook in module 8, which is the section on identities. Is that number 2 or 3? I think it's 3. What page are we? What is it? Module 8. 337. Okay, so I showed you the most commonly used identities, but there are dozens and dozens more. And so here are some examples of those. Look at tangent x times cotangent x over cosecant x. That's B. Do I have that written down right? Okay, so the idea with these is we can use other identities to simplify expressions. We can use other identities to simplify expressions or create new identities. Okay, so one technique, important technique, is change everything into sines and cosines. So one important technique is change everything into sines and cosines. So tangent x equals what in terms of sine and cosine? If it's opposite over hypotenuse, then it would also be sine over cosine, right? Sine over cosine. And we saw that cotangent is the reciprocal of tangent. It's the reciprocal of tangent. It's 1 over tangent. This is a new one we just talked about. And so if it's 1 over tangent, then what is it in terms of sine and cosine? Yeah, it's going to be the reciprocal, cosine over sine. And then what was 1 over cosecant? 1 over sine x. That was another one we just introduced. We said cosecant is by definition 1 over the sine. 1 over sine. Okay? So an important technique when you're working with these just identities is to change everything into sine and cosine. So what does our numerator become? We got sine over cosine times cosine over sine. That's just 1. And we have 1 over sine x, which is the same as sine x. Okay, so this is a new identity. Okay, maybe not a very useful one, but it is still an identity that tangent x, cotangent x over cosecant x equals sine x. That's an identity. That's an identity. What's another one on that page? What's that? Sine x. Oh, yeah, I need it, right? Okay, last one. So the next one is sine x times cotangent? Just tangent? Plus what? Plus cosine? So we're going to use our technique here, change everything into sine and cosine. Sine x times sine x over cosine. All right, this brings us to the next technique for these. The next technique, besides changing everything to sine and cosine, is get a common denominator and add fractions. That's the only thing we can do here. So we've got a fraction plus something else, so let's get a common denominator and make it all one big fraction. All right, so what will our common denominator be? Yeah, cosine. So we got cosine over here, so we're just going to make a common denominator of cosine on this one. We'll be able to add. So we'll have, this is actually sine squared, right? Sine squared x over cosine plus, what is cosine x with a common denominator of cosine x then? So it's like multiplying top and bottom by cosine. Cosine on top, cosine on the bottom gives us cosine squared. Then we're ready to add our fractions and make one big fraction. So our common denominator is cosine. And our numerator is sine squared x plus cosine squared x. Third technique, so first technique, change everything into sines and cosines. Second technique, when applicable, add fractions to make one big fraction. Last technique, use common identities that you know already. Do you see one? You should recognize what we're looking at there. Sine squared plus cosine squared. No matter what the angle measure is, that's always equal to 1. That's our Pythagorean identity, right? That's always equal to 1. So this is 1 over cosine. And we do it again. We recognize what is 1 over cosine? Secant x. Okay, so there's another identity. That sine x, tangent x, plus cosine x is the same as? For all angles. For all angle measures, those are equal. So that's a new identity. Okay, we'll start vectors on Wednesday.